Good evening, everyone. So, so I am Anchor Kartika. I am the TA for the NPTEL course Fluidization Engineering. So, the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. And I am a research scholar from Department of Chemical Engineering, IIT Hyderabad. So, I have been handling these live sessions where we solve the problems related to that week portion, which would be helpful for you guys in submitting the assignments promptly on time. So that is the motto behind our weekly sessions. So every week we have been having the classes from 3 p.m. to 5 p.m. As I mentioned in the last week's class that we are shifting the timings for today's class alone due to my some work. So like today's class we are having it from 6 p.m. to 8 p.m. Yeah. So we'll start the session without any further delay. So as we have been seeing every week, this is a 12 weeks course and we have seen almost from the introduction and now we are in the week 10 actually. So what we have seen is that we have seen the introduction to the fluidization, what fluidization is and what are the advantages and disadvantages of fluidized beds and what are the industrial applications of fluidized beds. So what is fluidization? Fluidization is nothing but the process in which we pass a fluid at a sufficiently high velocity so that the particle starts behaving like a fluid. They behave similar to the fluid by and therefore we gave the name fluidized beds. And what are the advantages? The advantages are that it can offer higher or enhanced heat and mass transfer rates because of the increased surface area. Similarly, we have disadvantages like attrition and loss of materials from the bed as we have seen in the last weeks and we will also be seeing in today's class. So later we have seen about the characteristics of solids and how we are classifying the solids based on the size and the relative density between the particles and the fluid. So Gelda classifies the particles into four classes A, B, C and D, and based on their size and density we have got those. For example, the smallest size particles comes under the Gelda C classification while the largest one comes under Gelda D. These particles behave differently, so it becomes necessary to have some sort of classification for the particles. Next is the flow pattern inside the fluidization. In terms of velocity, there is a difference in the movement of the solids inside the bed. Like velocity meaning the fluid inlet velocity, and by using that we can have a certain mapping regimes or flow regimes where we can see flow pattern from packed bed condition, and then we have a minimum fluidization condition, and later we have, if it is a liquid fluidized bed, we will be seeing homogeneous fluidization. If it is a gas solid fluidized beds, we will be having the presence of bubbles felt in the fluidized beds. Later we will also be having bubbling bits and slugging fluidization and turbulent fluidization, pneumatic transport when we pass the gas. So the bubble movement again becomes an important part that we have seen a separate week allotted for the bubbling fluidized bits. And also another important thing is the distributor system. type of distributors is also important, because only that controls the pressure of inside the system, and therefore economically viability of using the fluidized bed in the industry level is controlled by using the distributor. And last few weeks we have seen about the entrainment and alliteration, where the carryover of solids happens from the fluidized beds. And lastly it is about attrition mechanism, and later we'll see about the mass transfer and the heat transfer phenomena. So books and references, we have Cooney and Levenspil's Fluidization Engineering, which is covering almost all the basic concepts required to have the at this level for those who are interested in studying the fluidization and taking up future in fluidization. And next is Gidaspo's multiphase flow and fluidization, and third one is Gibelara's fluidization dynamics, and last one is SK Majumder's hydrodynamics and transport processes of inverse bubbly flows. I just put the animation and page number, which I think I forgot. So for the week 10, we are now going to question 1. In question 1, what is asked is that the breakage probability does not depend on dash. Option A, solid load. Option B, cyclone outlet gas velocity. Option C, particle size. Option D, material specific constant. So what do you think is the right answer, and why do you think so? Okay, so when we are saying about the breakage probability, it is mostly associated with the particle attrition happening inside the cyclone. So it is cyclone inlet gas velocity. I mean, what factors breakage probability depends on solid load S, and cyclone outlet gas velocity. This is a false one, because it depends on cyclone inlet gas velocity but not cyclone outlet gas velocity. And third one, it is particle size, true. And last one, it is material specific constant, that is also true. So we can say that it is, the answer is option B. We will be seeing a formula for the same in the coming up slides. But for now, it is cyclone outlet gas velocity is the answer. The breakage probability does not depend on cyclone outlet gas velocity. We'll move on to, as I mentioned, the answer is cyclone outlet gas velocity. So in question 2, it is about, under the same magnitude of breaking energy, the material which has the dominant fraction of surface area in a mixture, the attrition rate of this material is dash. Option A, depend on its particle size. Option B, depend on its particle porosity. Option C, independent on its particle size. Option D, none of the above. So the question I'll read once again. It is about under the same magnitude of breaking energy, the material which has the dominant fraction of the surface area in mixture, the attrition rate of this material is dash. So you think of the answer, I'll come in a minute. So I'll tell you the answer. The answer is independent on its particle size. Okay, I kept the slide on this position and I went. So you people would have seen the answer by now. Let it be. So what you need to carry away from this particular slide is that it is asking the questions about the material which has the dominant fraction of the surface area in the mixture. The attrition rate of this particular material is independent on its particle size because the material has the dominant fraction of the surface area in a mixture. So therefore, since it has the dominant fraction of the surface area in the mixture, it already has the dominant fraction of the surface area, so it further does not depend on its particle size. So we say that it is independent on its particle size is the right answer. Now, option C is the right answer. Let us go to question 3. In question 3, it is about which of the following model propose that the mass attrition rate is proportional to the volume or mass of the component independent of its particle size. So here a few models are given. From that we have to identify which model has proposed the following statement, that the mass attrition rate is proportional to the volume or mass of the component and it is independent of particle size. So we must be aware that mostly in this particular week's assignment problems, I have chosen mostly on theoretical questions with only one problem. So if you have any issues with that, we'll rectify it in the next week or in the coming up week. But for now, we have only one problem and the rest are theoretical questions. So that's what it is. And therefore now we'll go to question, I will look at the options, that is the models. So first one is Arena et al 1983, second one is Merrick's and Haley's excessive velocity model, third one is Chiron et al 1985 model, last one is Pan and Srivatsava's model. Answer is I think Pan and Srivatsava's model. So since I mentioned it is about the theoretical questions, I request you all to be kindly aware of all the concepts like who proposed what models and what are all the assumptions given in that model. When you are talking about models, it becomes very much necessary to know that what are all the assumptions in that particular model. The last few classes before, we have seen the bubble dynamics and bubble model, Davidson and Davidson's bubble model. So there were certain assumptions involved. So similar to that, you must be aware of all the assumptions involved in all the models. At least for those important models, you people must be aware of the assumptions involved. So for this question, let us go back and read the question once again. It is, which of the following model proposed that the mass attrition rate is proportional to the volume or mass of the component independent of the particle size? And the answer is Fan and Srivatsava's model. So option D is the right answer. Now let us go on to question 4. In question 4, it is mentioned that which of the following model proposes that the mass rate is proportional to volume or mass of the component independent of particle size? No. Just a minute, just give me a minute. So let us continue back. We'll go to question 5. Question 4, I'll come back again. Question 5. Which of the following assumption does not consider in the surface reaction model for attrition distribution? So, which of the following assumption does not consider in the surface reaction model for attribution rate distribution? Option A, abrasion is the dominant braking mechanism. Option B, materials involved have a natural grain size. Option C, particle mixture is uniformly mixed without any segregation. Option D, attrition property of each material can be commonly defined. So take a minute and answer the question correctly. Answer is option D. Attrition property of each material can be uniquely defined, not commonly defined. Okay, actually coming back to question 4, this particular statement is a wrong statement. It is not. Which of the following represents the relationship for the breakage rate for the particle? For the breakage rate of the particle, okay, time is actually running, so we'll quickly go through the content. Which of the following represents the relationship for the breakage of the particle psi, where dp is the particle diameter based on screen analysis, cm is the material constant, sm is the mass based specific energy, and k is the parameter that represents the distribution of defects on the particle surface. So first option A, it is psi is equal to 1 minus exponential of minus cm into dp square into sm to the power of 2 minus k by 5. Option B, psi is equal to 1 minus exponential of minus cm into dp square into sm into 2 plus k by 5. Option C, psi is equal to 1 plus exponential of minus cm into dp square into sm to the power of 2 plus k by 5. Option D, it is psi is equal to 1 plus exponential of minus cm into dp square into sm to the power of 2 minus k by 5. The right answer is option B is the right answer. Psi is equal to 1 minus exponential of minus cm into dp square into sm to the power of 2 plus k by 5. Option B is the right answer. So now we will go to question 5. In question 5, it is given that which of the following assumption does not consider in the surface reaction model for the attribution rate distribution. Attrition rate distribution. Attrition. So options are abrasion is the dominant breaking mechanism. Option B, materials involved have a natural grain size. Option C, particles mixture is uniformly mixed without any segregation. Option D, attrition mechanism of each material can be commonly defined. So we have seen that the right answer is option D, attrition mechanism of each material can be commonly defined. What and why is this assumption is not considered in the surface reaction model for attrition rate distribution? Because the statement should have been attrition property of each material can be uniquely defined, whereas here it is given as commonly defined. So therefore option D is the wrong statement. So we'll go to question 6. In question 6, it is given that the attrition can be minimized by dash. Option A, proper material selection. Option B, proper design of distribution. Option C, reducing the conveying velocity in case of attrition in pneumatic conveying. Option D, all of the above. So think logically, how can you minimize attrition? Option A, attrition can be minimized by proper material selection. Is that true? Yeah, it is true, because we can choose the material in such a way that it cannot undergo attrition in the system under our consideration. And second one, it is proper design of distribution, whereas this is also true. And third one, reducing the conveying velocity in case of attrition in pneumatic conveying. Again, this is also, if velocity is reduced in the pneumatic conveying transport, you can reduce the attrition. So option D is the right answer, all of the above. So we'll go to question 7. In question 7, it is given that according to the surface reaction model for a particle of radius I, actually, if you don't mind, I'll just switch off my video, because here it is bit difficult for me to I mean, I am having some network issues, so I am just switching off my video. I hope it is alright for you guys. So now I think we'll be able to cover the session without any difficulties. I am facing some network issues over here. And those controls. Okay, fine. We will continue with our session, and we are nearly in question 7. We have 10 more questions from this session, and the 15 more problems from the last week's assignment. So we'll quickly go through them, because I don't know when my network might go again. So coming back to question 7, it is according to the surface reaction model for particle of radius Ri and mass Mi, the mass attrition rate RTI and the fractional attrition rate is defined by dash. So here we are given three components. The first one is particles radius is known, particles mass is known, and the mass attrition rate is also known. Only unknown is fractional attrition rate. So option A, it is RTI is equal Ri is equal to RTI divided by Mi. Option B, Ri is equal to RTI square divided by Mi, and option C, Ri is equal to RTI by Mi square. Option D, it is Ri is equal to square root of RTI by Mi. So here we need to note two things. This capital R denotes the fractional attrition rate, and RTI denotes mass attrition rate. So since mass attrition rate is given and also the mass of the particle is given, the fractional attrition rate can be given by dividing the mass attrition rate divided by mass of the particle. So it is Ri is equal to RTI by Mi is the right answer. That is option A is the right answer. Now we'll go to question 8. In question 8, it is given that select factors affecting attrition. Option A, particle structure. Option B, pre-treatment of particle. Option C, particle shape. Option D, all of the above. So what do you think is the right answer? We all know that the right answer is all of the above. Why can anyone say that? Okay, I myself say that it is because we are here selecting the factors affecting the attrition. First one, particle structure can affect the attrition. If it is sharp, needle-sized structure, the chipping off of the particles might take place. And second, pre-treatment of particle, again, it might result in the damaging of the particle. And particle shape, particle structure, particle shape, everything plays a huge role. So therefore, the right answer is all of the above is the right answer. So coming to question 9. In question 9, in a solid mixing mechanism, the gas bubbles generally produce an upward drift to particles. Thus, to balance such upward movement, there is a mass circulation downward in the bubble-free region of the bed. Option A true, option B false. Yes, so what is being asked in the question is that the gas bubble produce an upward motion of the particles, and to balance such upward movement there is mass circulation downward in the bubble free region of the bed. Is this true or false? We all know that it is the true, because there is an upward drift and balance is created by the downward motion of the mass circulation of the particle in the bubble free region. So answer is actually true. Coming to question 10, it is here mentioned that vertical mixing is dash than the horizontal mixing. Option A faster, option B slower, option C same, option D none of the above. Generally, vertical mixing is faster than the horizontal mixing, because the chances of the particles getting mixed in the vertical region is quite high than the horizontal mixing. If you think logically, if you can imagine the conditions, you can say that vertical mixing is faster than the horizontal mixing. So coming to question 11, in question 11 it is given that select false statement from the following. Option A, the dispersion model does not always represent well the vertical mixing of solids. Option B, the dispersion model well represented the mixing during turbulent fluidization where the bed looked close to homogeneous. Option C, dispersion model is to represent reasonably the vertical mixing in tall beds in which rather small scale mixing is taking place. Option D, none of the above. Okay, so we are here to identify which of them is the wrong statement. So not I mean we are not going to identify which of them is the right statement. So think accordingly and read the statements one more time. We'll discuss. So now we are clear, I guess, if we think in that fashion. So a dispersion model does not always represent well the vertical mixing of solids. That is true, because it identifies, I mean, it is not always used to denote the vertical mixing. And second statement, it is well represents the mixing during turbulent fluidization where bed looks closer to homogeneous bed. And third one is dispersion model, is to represent reasonably the vertical mixing in tall beds in which rather small scale mixing is taking place. So all of them are true. So the false statement is not here. So the right answer is none of the above. Coming to question 12, in that it is that find the vertical dispersion coefficient in a small bed if gas velocity is 10 meter per second. So option A 0.56 meter square per second, option B 1.06 meter square per second, option C 0.106 meter square per second, option D 5.6 meter square per second. So this is what I was mentioning when I said there will be one problem involved in the whole week 10 assignment questions. So that problem is this problem. If you can identify, I would be happy. I mean, identify the method used to solve the problem. So I'll give you the answer even, but you guys take a minute time and come up with the answer. So what is the answer? It is option B is the right answer, that is 1.06 meter square per second. So take a minute and come up with the right answer. Time now was 6:47. I'll ask the question by 6:48. 1 minute for you, and is all. I'll give you an idea. So what are we asked to find? We are asked to find the vertical dispersion coefficient in a small bed, and we are given the gas velocity. So we all know to find the vertical dispersion coefficient, the formula involved is a very simple and straightforward one. So we'll go and see that solution. First we need to write the given, and given is that the gas velocity values are given, which is 10 meter per second, and we are asked to find vertical dispersion coefficient in a small bed. And now we are going to see about the formula. Formula is DSB is equal to vertical dispersion coefficient is equal to 0.06 plus zero point 0.1 into U in meter square per second. So I have given you the formula even. Now we are just required to find the answer. So DSP is equal to 0.06 into 0.1 into 10. 0.1 into 10 it gives you 1, plus 0.06 it gives you 1.06. So answer is 1.06 meter square per second. As I have mentioned, it is a very straightforward problem which will not require you to remember much except these coefficients, which is very much required to be remembered. I'll go back and give you the answer again. Find the vertical dispersion coefficient in a small bed if gas velocity is 10 meter per second. So answer is option A 0.56 meter square per second, option B 1.06 meter square per second, option C 0.106 meter square per second, and option D 5.6 meter square per second. And option is 1.06 meter square per second. What was the formula? It is 0.06 plus 10 into U. Sorry, U 0.1 into U. 0.06 plus 0.1 into U gives us the vertical dispersion coefficient in a small bed. So DSP is equal to 0.06 plus 0.1 into U. We know the value of U as 10, which gives the final answer as 1.06 meter square per second. So I hope you are clear with this. Now we'll go to question 13. In question 13, it is asked about the mean square horizontal shift of a particle passing through the bubble wake is directly proportional to dash. Option A, effective diameter of the wake. Option B, bubble diameter. Option C, bubble diameter square. Option D, none of the above. So the answer is, in the question it is asked about the mean square horizontal shift of particle passing through the bubble wake is directly proportional to, the answer is effective diameter of the wake square. So mean square horizontal shift of a particle passing through the bubble wake is directly proportional to effective diameter of the wake. Square of the effective diameter of the wake. Square of the effective diameter of the wake. Here square is there and it is proportional to square of the effective diameter of the wake. What is proportional to this? The mean square horizontal shift of particle passing through the bubble wake. So remember this. Now let us go on to question 14. In question 14 it is mentioned about fluidized bed reactor is used for mixed flow of solids. Option A true, option B false. We all know that the answer is true. Why? Because as I mentioned before, fluidized beds are used for mixing, segregation, whatever we require. Depending on the inlet velocity, we can control the mixing or segregation behavior inside the fluidized bed. So if you want mixing to happen, you can make it happen. So fluidized bed reactor is used for mixing of mixed flow of solids. So this particular statement is a true statement. Now let us go to question 15. In an actual practice where particles are continuously introduced and withdrawn, the bed turnover time and particle residence time plays an important role in governing the mixing characteristics of the fluidized bed. Choose the correct option. Option A, bed turnover time should be as short as compared to the particle residence time. Option B, bed turnover time should be greater than the particle residence time. Option C, bed turnover time should be equal to the particle residence time. Option D, none of the above. So here question is about in an actual practice where particles are continuously introduced and withdrawn, the bed turnover time and particle residence time plays an important role. So here, which is the correct statement? Bed turnover time should be as short as compared to the particle residence time, or bed turnover time should be greater than the particle residence time, or bed turnover time should be equal to the particle residence time, or none of the above. So the right answer is option A. Bed turnover time should be as short as compared to the particle residence time. So in continuous practice, both of them should be comparative, short as much as possible. So that is this. Now going on to question 16, we have that in segregation the term float sum represents dash. Option A, component that ultimately sinks. Option B, component that floats to the top of the bed. Option C, component that clusters together. Option D, none of the above. So flotsam is nothing but we have two components, flotsam and jetsam. So while segregating, we use these two terms to represent the component that floats to the top of the bed and that sinks to the bottom of the bed. So we have two terms, flotsam and jetsam. How do you remember that? So simple, flotsam means floating. So it refers to the component that floats to the top of the bed. Jetsam, it does not have anything, so it sinks to the top of the bed. Flotsam and jetsam. So remember that way. So for this particular question, in segregation, the term flotsam represents dash. And the answer is component that floats to the top of the bed. That is option B is the right answer. Now we'll go to question 14. In question 17, question 17 states that in a segregating fluidized bed, gas fluidized bed, mixing index can be represented as dash. Option A, mass fraction of jetsam in the top portion of the bed divided by jetsam mass fraction in the perfectly mixed bed. Option B, jetsam mass fraction in a perfectly mixed bed and mass fraction of jetsam in the top portion of the bed. And option C, mass fraction of flotsam mass fraction in a perfectly mixed bed and divided by mass fraction of jetsam in top portion of the bed. Option D, it is mass fraction of jetsam in the bottom portion of the bed divided by jetsam mass fraction in a partially mixed bed. So what do you think is the right definition of the mixing index? Mixing index is actually represented by mass fraction of jetsam in the top portion of the bed divided by jetsam mass fraction in a perfectly mixed bed. So option A is the right answer. So now we'll see how it exactly gives the mixing index. So we all know if mixing index m is equal to 1, it represents complete mixing, and if m is equal to 0, it represents it represents complete segregation. And here it is given mass fraction of jetsam in top portion of the bed and divided by jetsam mass fraction in a completely mixed bed. So what we all know that we have two components, that is the flotsam and the jetsam. So jetsam sinks to the top of bottom of the bed, while flotsam remains in the top of the bed, right? If we take bed like this, and if it is a complete segregation, we can see flotsam going to the top and jetsam going to the bottom. So what will happen? Mass fraction of jetsam in top portion of the bed, it becomes 0. Because in the top portion jetsam is not present, it becomes 0, and jetsam mass fraction in a perfect mixed bed. So if the bed is perfectly mixed, we have that jetsam is equally distributed throughout. So it represents, I mean, some mass fractions, let it be. If it is a segregated one, we have the jetsam, we do not have jetsam in the top portion, so the numerator becomes 0. Whereas if it is a completely mixed bed, the numerator and the denominator would be same. Mass fraction of jetsam in top portion of the bed is same as the jetsam mass fraction in a perfectly mixed bed. So that time it becomes 1. So if it is 1, it is a completely mixed bed. If it is 0, it is a completely segregated bed. Second one, so we all know this is the first one and this is the right statement. Just for our clarification, we will see jetsam mass fraction in a perfect mixed bed divided by mass fraction of jetsam in the top portion of the bed. So does not give the right value because sometimes it can be divided by 0 and we will be getting a wrong values. So this one is a false one. So option C, flotsam mass fraction in a perfectly mixed bed divided by mass fraction of jetsam in the top portion of the bed. So actually these two are not, we are not able to denote, we cannot actually compare these two. Like it should be same in the numerator and denominator, so therefore which again cannot be used for the calculation. And option D, it is mass fraction of jetsam in the bottom portion of the bed divided by jetsam mass fraction in a partially mixed bed. Again this is false. Why? Because mass fraction of jetsam in the bottom portion of the bed and divided by jetsam mass fraction in a partially mixed bed. Again we cannot compare with the partially mixed bed, and mass fraction of in the bottom portion of the bed might be higher than the jetsam mass fraction in the partially mixed bed, so it would not give us a proper accounting. So the proper accounting of the mixing index is actually given by option A, which represents a mass fraction of the jetsam in the top portion of the bed divided by jetsam mass fraction in a perfectly mixed bed. So option A is the right answer. Now we'll go to question 18. In question 18 it is given that in the segregation index choose the correct option. So last question it was about mixing index, here it is about segregation index. So option A, S is equal to 1 represents a state of perfect mixing. Option B, S is equal to 0 represents a state of perfect mixing. Option C, S is equal to 1 represents a state of complete segregation. And option D, none of the above. So answer is option C. Oh, option A. Okay, option A is the right answer. S is equal to 1 represents a state of perfect mixing. Just give me a moment. I'm just looking at the formula for segregation. So it would be helpful when I mention that. Okay, segregation index is nothing but it is the ratio of mass fraction of flotsam in the top portion of the bed divided by flotsam mass fraction in a perfect mixed bed. So there we have seen about the jetsam, here it is about flotsam. So if it is float segregation index, it is about mass fraction of flotsam in the top portion of the bed divided by mass fraction of flotsam in the perfectly mixed bed. So if it is 1, again it represents the state of perfect mixing, similar to how we have defined the jetsam mass fraction in the bottom portion of the bed divided by the, I mean, jetsam mass fraction in top portion of the bed divided by jetsam mass fraction in a perfectly mixed bed. So if it is 1, it represents the state of perfect mixing. And what do we have if it is a state of complete segregation? We have it as 1 minus XSF. XSF is nothing but it is the mass fraction of the component in the of the flotsam mass fraction in the perfect mixed bed is given by XSF. So the 1 by XSF gives the state of complete segregation. So here S is equal to 1 represents perfect mixing, and similarly mixing index 1 also denotes complete mixing. So be clear in that. Now we will go to question 19. In question 19 it is given that how can one alter the interchange rate of solids between stages? Option A, high gas velocity must be matched with an increased freeboard. Option B, bigger baffle openings must be matched by smaller freeboard. Option C, for different baffle spacing, the same freeboard height gives the same solid interchange. Option D, all of the above. So what is the question? In this question it is about how can one alter the interchange rate of solids between stages. Option A, it is high gas velocity must be matched with an increase in freeboard. Option B, bigger baffle openings must be matched by smaller freeboard. And option C, it is for different baffle spacing the same freeboard height gives the same solid interchange. So here all of the above is the right answer. It is about using multiple stages in the bed. So we'll go to question 20. In 20, bed levels must be adjusted to accommodate changes in gas and solid flow rates. Select the correct option. Option A true, option B false. Option A is the right answer. That is, statement is true. How? Bed levels must be adjusted to accommodate changes in gas and solid flow rates. As we have seen that increase in the gas flow rate, it might lead to pneumatic conveying. The same bed which was like in this homogeneous fluidization condition at the low fluid velocity becomes pneumatic conveying at the higher fluid velocity. So it becomes necessary that we adjust the bed height up to accommodate the changes in the gas and the solid flow rates. So answer is option A, that is true, is the right statement. So 20 questions are from week 10. Now we have some 15 problems from last week, that is week 9, entrainment, elucidation, attrition. Those mechanisms. Assignment problems from week 9 which you would have submitted by this Wednesday, and these are the solutions for that which we can discuss. And option some few points to recollect: in a vigorously fluidized bed, solid particles are ejected and entrained from the dense bed. These particles then enter the freeboard bed, the space between the bed surface and the gas outlet. So I hope that all these concepts are very familiar to you, because we have been seeing and studying this in the last class very clearly. And option C, it is these particles can leave the freeboard and escape from the unit depending on the size of the freeboard and the velocity of the fluid. Option D, this results in loss of valuable materials. So all these things we know them, and it is just a quick revision. Now we'll start with question 1. In question 1, it is given what is the correct unit of entrainment in the fluidized bed reactor. Option A, kg per meter cube per second cube. Option B, kg per meter square per second square. Option C, kg per meter square meter cube per second. Option D, kg per meter squares per second. Option D is the right answer, kg per meter square per second. How it is? Entrainment is the carryover of solids from the fluidized bed. When the velocity exceeds the terminal velocity of the particle would be removed from the bed. So it is a carryover of the particle per unit time per unit area. So it is kg per meter square per second is the right answer. We'll go to question 2. It is the flux of the solids. Flux of the solids carried out of the fluidized bed by the gas in kg per unit cross-sectional area per second. So as I mentioned, it is the formula. So it is kg per meter square per second is the right answer. Now we'll go to question 2. In question 2, choose the correct option. 1, splash zone. 2, dense bubbling phase zone. 3, lean or dispersed phase zone. Okay, in the right hand side we are given bulk density remains almost constant. Demarcation between the bed and the freeboard. Bulk density of solid decreases with height. Bulk density of solid increases with height. So can you guys match them? Okay, so first one it is splash zone. Options also I'll give. Option A 1Q 2R 3P. Option B 1P 2Q 3R. Option C 1Q 2P 3S. Option D 1Q 2P 3R. So can you guess the right answer? Okay, we'll just discuss the answer now. So option in the first one it is given about splash zone. So splash zone is actually the demarcation between bed and the freeboard. So one is option Q. Second one, dense bubbling phase zone, where the bulk density remains almost constant. And third one is lean or dispersed phase zone, where bulk density decreases with height. So it is Q, P and R. Q, P and R. I guess the answer is option D. Option D, Q, P and R, because we'll see now it is splash zone. It is the demarcation between the dense zone and the lean zone. Dense zone, the density of the particle remains a constant. In free zone, what do we call it as free zone? Free board. The bulk density decreases with height. So I hope you are clear now. We'll go to question 3. Okay. It is dense phase. It is lean phase or freeboard height, and where we are able to see the density decreases with height. Here the density is constant, and here we have the demarcation between the dense phase and the lean phase. So these pictures are taken from the NPTEL course slides and lecture slides. Now let us go to question 3. In question, okay, we have some small explanation. A dense bubbling phase, lean bubbling phase, freeboard. Freeboard is the section of the vessel between the surface of the dense phase and the gas exiting and the exiting gas stream from the vessel. And freeboard allows solids to separate from the gas stream. And transport disengaging height is the freeboard height above which entrainment is constant. Here after this the entrainment rate is constant. That is known as, above this height, above TDH, transport is constant, whereas below it is varying. The freeboard height above which entrainment is constant. Question 3. Select the correct option regarding the influence of gas density and bulk density of solid on the entrainment rate. Option A. Entrainment rate increases with an increase in the bulk density of solid. Option B. Entrainment rate decreases with an increase in the bulk density of the solid. Option C. Entrainment rate decreases with an increase in the gas density. Option D. Both B and C are correct. So here we are asked to identify the effect of gas density and gas bulk density of solid on the entrainment rate. So entrainment rate increases with an increase in the bulk density of solid, false. Entrainment rate decreases with the increase in the bulk density. Heavier particle tends to settle down, the lighter particles tends to flow up. So option B is true. Option C, if we look at it, entrainment rate decreases with increase in gas density. Again, with increase in the gas density. Note the point clearly, it is gas density. So with increase in gas density, again we are able to observe the decrease in the entrainment rate. So answer to this is both options B and C are correct. Now we see question 4. In question 4, select the correct answer concerning the effect of particle size and fraction of ions on the entrainment rate. Option A, entrainment rate marginally influenced by changing the size of the course material. Option B, entrainment rate is unaffected by the fraction of ions in the bed. Option C, both A and B are correct. Option D, none of the above. So first, when we look at it, here we are asked to identify the correct answer, where we are dealing with effect of the particle size and fraction of ions on the entrainment rate. So entrainment rate is there. What is the effect of particle size and the fraction of ions? So option A, it is entrainment rate marginally influenced by changing the size of the course material. And option B, entrainment rate unaffected by the fraction of ions in the bed. C is the right answer, because entrainment rate is marginally influenced by changing the size of the course material. Yes, it is true. And second one, it is unaffected by the fraction of ions in the bed. Like if ions are there, it is the chances of it getting entrained is there, but fraction of ions in the bed does not in any way influence the entrainment rate. So that is why answer is option C. Now we'll go to question 5. In question 5, axial distribution of solid as per Lee and Quack 1980 can be expressed as dash. Option A, epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to minus or exponential of minus z minus zi into z naught. Option B, epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to exponential of minus z plus zi divided by z naught. Option C, epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to exponential of minus of z minus zi divided by z naught. Option D, epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to exponential of z minus zi divided by z naught. So here the answer is actually option C. Epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to exponential of minus of z minus zi by z naught is the right answer. So option C is the right answer. We'll go to question 6. In question 6, which of the following statement is true? entrainment flux increases with the pressure. Option B, entrainment flux decreases with pressure. Option C, entrainment flux is independent of pressure. Option D, none of the above. So, which of the following statement is true? Entrainment flux decreases with pressure. Okay, increases with pressure. Okay, entrainment flux increases with pressure is the right answer. We'll go to question 7. So, seventh question is a problem. Since this problem is from last week assignment, I haven't mentioned it. I was mentioning one problem which is concerned with week 10. So coming back to this problem, flux of solids carried out of the fluidized bed by the gas is 200 kg per meter square second. Calculate the slip velocity. So we are given the density of solids as 3000 kg per meter cube and epsilon SE is 0.04. And options are option A, it is 1.67 meter per second. Option B, 3.55 meter per second. Option C, 4.5 meter per second. Option D, 0.67 meter per second. So again, flux of the solids carried out of the bed is given as 200 kg per meter square second, and we are asked to find the slip velocity of the particles. We are asked to find the slip velocity. Given that density of solids is given as 3000 kg per meter cube and epsilon SE is given as 0.04. So we are asked to find the slip velocity. So answer is 1.67 meter per second. How it is, we'll see. So how are we going to do that? First, let us write the given. We are given the flux, which is 200 kg per meter square second, and entrainment flux, density of solids, and epsilon SE 0.04. And solid fraction over there is 0.04. And we are asked to find the slip velocity US. And for that solution, it is GSE is equal to rho S into epsilon SE into US. And US is equal to GSE divided by rho S into epsilon SE. And GSE we know it as 200 divided by rho S is 3000 and epsilon SE is 0.04. 3000 into 0.04, 200, we can cancel two zeros and one zero will go 0.4. 3 into 0.4 becomes 1.2 and 2 divided by 1.2 or 1 divided by 0.6. So it is 1.666 meter per second. So is that true? 1.67 meter per second is the right answer. Now again, if we see flux of solids carried out of the fluidized bed by the gas is 200 kg per meter square second and its slip velocity is what we have to calculate. Given the density of solids and the solid fraction epsilon SE, that is 0.04, and GSE is equal to 200 kg per meter square second and rho S is 3000 kg per meter cube and epsilon SE is 0.04. To find a slip velocity, And solution, we are finding GSE is equal to rho s into epsilon SE into US, and US is equal to GSE divided by rho s into epsilon SE, and we are substituting all the values and we are getting the final answer as 1.67 meter per second. I hope the question 7 is clear. Now we are going to question 8. In question 8 it is given that velocity of the gas in the fluidized bed reactor of dimension 0.7 meter, of diameter 0.7 meter is 1.5 meter per second, and fraction of the particles at the column exit is 0.06, and the measured particle velocity is 0.1 meter per second. Calculate the slip velocity. Option A, US is equal to 1.5 meter per second. Option B, US is equal to 2.55 meter per second. Option C, US is equal to 0.5 meter per second. Option D, US is equal to 3.15 meter per second. Actually, these questions and these problems, you must be telling me the answer, and I should be writing it down step by step, because all these problems you have submitted in the week's 9 assignment and you would have got the answer by now. So by now you people should have, like, okay, this is how it is done. If you had done it wrong, or if you had done it right, you should be like, okay, this should be done like this, and that is how I did it correctly. So those things should be coming out, but you people are not responding to any of my questions or whatever things. So it is a bit difficult. It is like talking one way, one side. Okay. So in this question, what is given is that the velocity of the gas in the fluidized bed reactor for diameter 0.7 meter, diameter of the column is 0.7 meter, and the velocity of the gas is 1.5 meter per second. Fraction of particles at the column exit is 0.06, and the measured particle velocity is 0.1 meter per second. We are asked to find the slip velocity. Now we'll see the option first. It is 1.5 meter per second, and now let us look at how to calculate it. First, let us write the given. It is bed diameter is 0.7 meter and gas velocity is 1.5 meter per second, and solid fraction is 0.06 and particle velocity is 0.1 meter per second. Solid fraction, column exit is 0.06, and yeah, we are asked to find the slip velocity. And US is equal to UG divided by 1 minus epsilon SE minus UP. UG is 1.5 minus 0.1. It would be mostly 1.5 divided by 1 minus 0.06. It 1.5 divided by 0.94 minus 0.1. So it is giving us 1.4957. So it is roughly 1.5 meter per second. Also, you can see that slip velocity is gas velocity minus particle velocity. So gas velocity, we are calculating it as the gas velocity divided by the solid fraction of the gas at the column exit. So it is gas velocity UG divided by 1 minus epsilon SE, that is 0.06, and therefore you will be getting the 0.06, 1.94, 1.5 divided by 0.94. So we will get the value as 1.50 meter per second. So it's a very simple straightforward problem again. Now we will go to question 9. In question 9, choose the correct option for fraction of the particles at the column exit if the fine particles velocity is very high and an epsilon SE is less than 1. So epsilon SE is equal to GS divided by rho S into U plus UP, and here U is the finer, if fine particles U is very high, and epsilon SE is approximately GS divided by rho S into U minus UP, and GS is equal to, epsilon SE is equal to rho S divided by GS into U minus UP. Option D, none of the above. So it is GS is equal to rho S US epsilon SC we have seen, and US is equal to U minus UP. So option B is the right answer. Epsilon SC is equal to GS divided by rho S into U minus UP. So in other words, we can write it as GS is equal to epsilon SC into rho S into US. US is nothing but U minus UP. I hope it is clear. We'll go to question 10. In 10th question, according to the freeboard entrainment model of Cooney-Levenspiel, the model distribution can be, solid distribution can be defined as dash. Epsilon S minus epsilon S star divided by epsilon SD minus epsilon S star is equal to exponential of minus A into ZF, and epsilon S minus epsilon S star divided by epsilon SD minus epsilon S star is equal to exponential of minus Z I divided by Z naught. And third one, it is epsilon S minus epsilon SD, epsilon S minus epsilon S star divided by epsilon SD minus epsilon S star is equal to exponential of A into ZF. And option D, none of the above. So answer is option A. Epsilon S minus epsilon S star divided by epsilon SD minus epsilon S star is equal to exponential of minus A into ZF. This is according to the freeboard entrainment model of Cooney and Levenspiel, where we are giving the solid distribution using this particular formula. One more thing we need to know is the second option. You have seen it somewhere. Do you guys remember where it is? So these are all repetitive questions actually, frankly to say. So it is according to Lee and Quark. Epsilon S minus epsilon S star divided by epsilon SD minus epsilon S star is equal to exponential of minus Z by Zi divided by Z naught. The same question is same option is only given over here, given over there. So you must be aware of Lee and Quark axial distribution of solid and Cooney and Levenspiel's freeboard entrainment model. Similarly, this one US is equal to GS by rho S epsilon SC, and this is what is asked over here also. Like be clear in whatever you mention, and that is one thing. Option A here, it is Cooney-Levenspiel's freeboard entrainment model. So I hope it is clear now. Okay, so it is Cooney-Levenspiel's freeboard entrainment model. Here we are able to see dense bed, and freeboard entrainment model is given by, they have mentioned three things. One is the upward moving agglomerate and downward moving agglomerate and upward moving dispersed solids. So I hope you guys remember those. Now let us go to question 11. In question 11, it is like, determine the bed height at a minimum fluidization. And it is given epsilon mf is 0.55, epsilon sd is 0.22, epsilon se is 0.05, a is 1.45 per meter, and ht is 12 meter, hf is 1.01 meter, epsilon s star is equal to 0.01. Option A, LMF is equal to 3.25 meter. Option B, 7.51 meter. Option C, 8.50 meter. Option D, 5.66 meter. So answer is 5.66 meter. So we will see how to calculate that. What are all the things given? Minimum fluidization, at the condition of minimum fluidization, void fraction is given, and solid fraction at dense bed, and the exit condition is given. A is given, HT is given, HF is given, epsilon S star is given. So we'll go and see solution. First we have written all the given things, and second to find LMF. Third, Solution: LMF is into 1 minus epsilon MF is equal to epsilon SD minus epsilon SE divided by A plus HT into epsilon SD minus HF into epsilon SD minus epsilon S star, and LMF into 1 minus epsilon MF is equal to epsilon SD is 0.22 and minus epsilon SE is 0.05 divided by 1.45 plus HT is 12 into 0.22 minus HF is 1.01 into 0.22 minus 0.01. So we are getting this particular term is giving us 0.1172 plus 2.64 minus 0.2121. Finally, we are getting it as 2.5451. LMF is equal to this particular value divided by 1 minus epsilon MF. Epsilon MF is given as 0.55 and therefore it is 1 minus 0.55, which is giving us 5.6557 meter. Rounding off, we are getting it as 5.66 meter. So here it is the formula which you must be knowing. Only then you can solve the problem. So even though it looks simple, it is not. Epsilon MF, everything we know and we know how to solve it. Right? I hope it is clear now. If you want, you can read the question once again. It is just a direct substitution. For you to know how to get the right answer, you must be aware of the formula. That is the only thing which is bit tricky in this particular problem. So I hope it is clear. Now we'll go to question 12. Calculate the freeboard height, and data is epsilon S star is equal to 0.01, epsilon SE is equal to 0.05, epsilon SD is equal to 0.2, A is 1.8 per meter. Now we are asked to find the freeboard height. So epsilon S minus epsilon S star divided by epsilon SD minus epsilon SE is equal to A into, exponential of minus A into Z, I guess that is the formula. And HF is equal to 0.2 meter, HF is equal to 1.05 meter, HF is equal to 0.87 meter, and HF is equal to 0.5 meter. Answer is HF is equal to 0.87 meter. We will see how. So first we are writing given epsilon S star, epsilon SE, epsilon SG and A is given. And second we are to find HF, and third one we are giving the formula, and more than formula I think it should be a solution. Epsilon S minus epsilon S star divided by epsilon SD minus epsilon S star is equal to exponential of minus A into HF. So here we know everything: epsilon S, epsilon S star, epsilon SD, epsilon S star, and A is known, HF is unknown. So remaining, leaving out, we are calculating everything. You can more than, why to eliminate it? We put solution and we'll write this again. It should be simple now. Yeah. I hope it is clear now. If you want to just go through it for a minute, we will see how to do the next question. Okay. So we'll go to question 30. In a fluidized bed reactor of column diameter 0.32 meter, the gas flow rate is 100 liters per minute. Calculate the superficial gas velocity in mm per second. So here what are we given? We are given the column diameter, which is 0.32 meter, and gas flow rate is given as 100 liters per minute. We are asked to find the superficial gas velocity. It is a very simple question. I don't know. Option A 5.25 mm per second. Option B 25.50 mm per second. Option C 10.9 mm per second. Option D 20.72 mm per second. So answer is option D 20.72 mm per second. So we'll see how to solve that. Q is flow rate is given as 100 liters per minute and diameter of column is given as 0.32 meter, and we are asked to find the superficial gas velocity. Now USG is equal to Q by area of the column. Q is 100 liters per minute. 100 into 1 liter is equal to 10 power minus 3 meter cube. So 100 into liter per minute, we are converting into 100 into meter cube per second. So 100 into 10 power minus 3 meter cube divided by 60 seconds and divided by area of the column, which is nothing but pi by 4 d square. So 3.14 divided by 4 into 0.32 square. So we are getting the value as 20.7297 into 10 power minus 3 meter per second, which if we substitute it in the formula back, we are getting the, if we use the 10 power minus 3 meter per second as mm per second, we are getting the value as 20.72 mm per second. So again, we can see the question 13. It is a very straightforward problem where we are asked to find the superficial gas velocity given the values of diameter of the column and the gas flow rate. So gas flow rate is given in a liter per minute. So we are converting it into meter cube per second by multiplying it by 10 power minus 3 and dividing it by 60. And superficial gas velocity is obtained by dividing the flow rate by area of the column, and therefore it is 100 into 10 power minus 3 meter cube per second 60 second in divided by 3.14 by 4 into 0.32 square. So we are getting the value as 20.72 mm per second. I hope it is clear. Now we'll go to question 14. Calculate the height of the column if the height of the lower dense bed is 5.4 meter and the freeboard height is 1.15 meter. So we are asked to find the height of the column given that the lower dense bed is 5.4 meter and freeboard height is 1.15 meter. So answer is HT is equal to 6.55 meter. Option B, HT is equal to 12.55 meter. Option C, HT is equal to 3.25 meter. Option D, HT is equal to 9.30 meter. So answer is actually option A, HT is equal to 6.55 meter. To find the solution, first let us write given. HT is equal to 5.4 meter and HF is equal to 1.15 meter. Dense bed is 5.4 meter and freeboard height is 1.15 meter. And we are asked to find the total bed height HT, and HT is equal to HF by HT. So it is 5.4 plus 1.415 it is 6.55 meters. So again it is the simplest problem where we are asked to find the height of the column given the height of the lower dense bed region and the height of the freeboard region. So if we go back, so now I think it would be very clear. We are just adding the dense face column height and the freeboard column height. So yeah, it is a very simple problem. Now we are asked to find, select the wrong statement or regarding the entrainment. Option A, entrainment is independent of size for units larger than 0.1 meter in diameter. Option B, entrainment flux increases with an increase in the bed height. Option C, entrainment rate decreases as the superficial gas velocity increases. None of the above. I think it is D or C. Okay, actually we are asked to find the wrong statement. So if we look at it, first let us see how the statements are given. The first statement is option A, entrainment is independent of size for units larger than 0.1 meters. So this is true because when column size is larger than 0.1 in diameter, entrainment rate is independent of the size. And second, that is true. Second one, it is entrainment flux increases with increase in the bed height. So again that is true. And third one, when you are increasing the particle bed height, it is affecting the entrainment rate, entrainment flux, and it is increasing the entrainment flux. And third one, entrainment rate decreases as the superficial gas velocity increases. As the superficial gas velocity increases, the entrainment rate increases. The when velocity is high, the carryover of the particle is high. So entrainment flux increases as the superficial gas velocity increases is the right statement, whereas the one given over here is a false statement. So therefore option C is the wrong statement. So in this question we are asked to find the wrong statement. Be clear, we are asked to find the wrong statement regarding the entrainment, and we have rightly identified it as the entrainment rate decreases as the superficial gas velocity increases, because it should have been the other way round. And now yeah, thank you so much. Now the time is 7:43. We have 15 more minutes left, so I would like to take any feedback from you guys, or if there is any doubts from today's session, please let me know. And in the meantime, I can give you a quick revision of the today's class, and we can have 5 minutes for discussion. Later we can close the session. So in today's session, we have seen 20 problems from week 10 and 15 problems from week 9 assignment. So week 10 it is mostly about attrition mechanism, and week 9 it is about entrainment mechanism. So here the breakage probability does not depend on the cyclone outlet gas velocity. It depends on cyclone inlet gas velocity but not outlet gas velocity. And under the same magnitude of the breaking energy, the material which has the dominant fraction of the surface area in the mixture, attrition rate is independent on its particle size, because it already has the dominant fraction of the particle size, surface area in the mixture. It already has the dominant fraction of the surface area, so therefore it does not depend on its particle size. It is independent on its particle size is the right answer. And now it is about following. Propose the mass attrition rate is proportional to volume or mass component of the mass of the component independent of particle size. So they propose that mass attrition rate is proportional to volume or mass of the component, but it is independent of its particle size. Who proposed this? Fan and Srivastava's model is the one which has this particular statement. And lastly, we have seen the psi expression. Psi is the breakage rate of the particle. Psi is equal to 1 minus exponential of minus cm into dp square into sm to the power of 2 plus k by 5. So that is, and later we saw about the assumption, which is not considered in the surface reaction model for attrition rate distribution. It is that attrition property of each material can be uniquely defined. It cannot be commonly defined. So that is the first statement. So because it should be coming as uniquely, it should not be commonly. So that is a mistake over in the D statement. Now it is about attrition can be minimized by all of these: proper material selection, proper design of distribution, and reducing the conveying velocity in case of attrition in pneumatic conveying. And lastly, it is about according to surface reaction model, for a particle of radius Ri and mass Mi, the mass attrition rate Rti, the fractional attrition is equal to mass attrition rate divided by mass of the component. Rti divided by Mi is the right answer. And selecting factors affecting attrition, it is particle structure, particle shape, pre-treatment of particles, all of these affect the attrition rate. And lastly, it is about solid mixing mechanism. The gas bubbles produce an upward drift flow, and to balance that there is a mass circulation downward also. So it is a true statement. And 10th one, vertical mixing is more than the horizontal mixing, or it should be faster than the horizontal mixing. And question 11, select false statement. The dispersion model, none of the above is the right answer, because all these are true statements. Dispersion model does not always predict well the vertical mixing of the solids. It does all, but it well represents the mixing during turbulent fluidization when the bed looked close to homogeneous. And dispersion model is to represent reasonably the vertical mixing in tall beds in which rather small scale mixing is taking place. So that is the thing. And question 12, it is about a problem where we are asked to find the vertical dispersion coefficient in a small bed if gas velocity is given. So DSB is equal to 0.06 plus 0.1 into U. Here U is 10, so we got the value as 1.06 meter square per second. Vertical dispersion coefficient. Mean square horizontal shift of particle passing through a bubble wake is proportional to the square of the effective diameter of the wake. It is about fluidized bed reactor is used for mixed flow of solids. True. And in actual practice, particles are continuously introduced and withdrawn. The bed turnover and particle residence time should be as short as possible. That is a statement. Flotsam is the particle that floats to the top of the bed. Jetsam is the one that sinks to the bottom of the column. So segregation rate, mixing index can be represented as mass fraction of jetsam in the top portion of the bed divided by jetsam mass fraction in a perfect mixed bed. Similarly, segregation index is represented as mass fraction of jetsam in the mass fraction of flotsam in the top portion of the bed divided by flotsam mass fraction in the perfectly mixed bed. And S is 1 represents the perfect mixing state. Similarly, M is equal to 1 represents the perfect mixing state, and M0 represents complete segregation, and S is equal to 1 by XSF. XSF represents the complete segregation. So answer is option A. And how can we alter the interchange rate of solids between stages? High gas velocity must be matched with increased freeboard, and bigger baffle openings must be matched with smaller freeboard, and for different baffle spacing, same freeboard height gives the same solid interchange. All of the above is the right answer. Bed levels must be adjusted to accommodate changes in gas and solid flow rates. That is a true statement. These are the problems from week 10. Later we have seen the entrainment and elucidation attrition problems. So for that, it is we have seen about some introduction, and unit of entrainment, it is the flux. So it is carryover of solids in kgs per unit area of, per unit cross sectional area per unit time. So it is kg per meter square per second. And splash zone is the demarcation between the dense zone and the lean or freeboard height. In lean or freeboard height, we are able to see density decreases with the height, whereas in the bulk density remains a constant. And this we have seen with respect to the image as well. Here it is density is constant. Here we are able to see density decreases with time, with height. So that is lean phase or freeboard height, and this is dense phase. So those are the things, and I hope it is clear. Now we are going to see regions in fluidization vessel. And okay, just a definition. An entrainment decreases with increase in gas density, and it decreases with increase in bulk density. So option C, B and B are right. And later it is about entrainment is marginally influenced by changing size of the course material. It is unaffected by the fraction of fines. Both are true statements. Leak-Quack, it is epsilon s minus epsilon s star divided by epsilon sd minus epsilon s star is equal to exponential of minus of z minus zi into z naught. And this is Lee and Quack. If exponential of minus a into zf is given, it is a Cunningham-Lenz's freeboard entrainment model. So please remember all the model equations and which corresponding model it represents. So that is one thing. And entrainment plates increases with pressure is a statement, and it is about a problem where we are asked to find slip velocity gs is equal to rho s into us into epsilon sc. On substituting, we are able to get the slip velocity. Us is the slip velocity. And another problem, it is u is us is equal to u minus up. U is ug by 1 minus epsilon se, and we are substituting everything, we are getting the value of slip velocity. And epsilon se is equal to approximately gsc by rho s into u minus us is the right answer. I mean u minus up. Technically it is us is the formula. Gs is equal to rho s into epsilon se into us, whereas epsilon se, if you want to get, it is gs by rho s into us. So that is option B. And question 10, it is we have seen already. Again, it is a formula where we need to find the problem where we are asked to find the minimum fluidization bed height, and we have done that rightly. And for that, this is the formula LMF into 1 minus epsilon MF is equal to epsilon SD divided by 1 minus epsilon SD minus epsilon SC divided by A plus HT into epsilon SD minus HF into epsilon SD minus epsilon S star. So we are just calculating everything, substituting everything and calculating the right answer. And it is about calculation of freeboard height. Freeboard height is nothing but again given according to Cunningham-Lenz's freeboard height model, and we are able to find the freeboard height. And later is about USG, that is superficial gas velocity, and we are given the column height and the flow rate. So flow rate divided by the area of the column gives the superficial gas velocity, which we have done clearly. And last before question is about calculation of the total bed height, freeboard height and the dense bed height is given. So it is just the sum of the both gives the total height of the column. And rank statement, it is about entrainment size is independent of size for units larger than 0.1 in meter diameter. Entrainment flux increases with an increase in bed height. So this is second statement is actually true. Third one, it is decreases as superficial gas velocity increases. That is the wrong statement. Entrainment rate actually increases with increase in superficial gas velocity. So option C is the right answer. So that's all for today's class actually. I thank everyone for attending. If you have any doubts, I will stay in the call for 5 more minutes and we can discuss, or else we can close the session also, because already the time now is 7:54. Okay, the thing I need to remember you guys is that this session from 6 to 8 p.m. is only for today's class, and then from the next week, that is from the coming week, we'll go back to our regular routine, that is 3 p.m. to 5 p.m. class. We'll go back. So we have 2 more classes, and I am planning to take 1 more additional class where we can see the summary of the session, and we can also discuss few problems, so that you can just consider it as a quick revision for you guys before you people appear for the exam, final exam. So final exam, as I am reminding every week, it is a combination of the NSEM exam. Along with that, you will have certain weightage from the assignments as well. So submit the assignments on time and get regular feedbacks, and also prepare for the exam, final exam. If you are appearing for exam, be careful of that as well. Like it is also important to perform well in the exams. So yeah, that's it for today's class. If there is any doubts, let me know, or else you can close the session. Okay. Mm, it appears that no one is interested. When did the call cut? Okay, actually the call got cut. I don't know when did it happen. But anyways, I think we are done with today's session also, so it is not an issue. Like there was some issue in today's internet from my end, so I joined through my mobile network, which is again worst. Like even though I have a lot of data, I'm not getting signal anywhere in here or in anywhere. So I'll not make any excuse the next time because I'll try to make an alternate arrangement. Please excuse for today's class, and thank you, and sorry for any inconvenience caused to anyone. I'll try to rectify from next class. Thank you, thanks again, once again, thank you.